So our question states that a stone is thrown in a puddle and the ripples spread out in circles, the radii of which grow at a rate of 4 centimeters per second. Okay, so there's an important bit of information here. Additionally, we know that the shape here, it's a circle that we're working with. Find the rate of increase of the area of the circular ripple when its radius is 20 centimeters. Okay, so what we're going to do here, let's identify the things that we know here. Now, first of all, what we've got here is we throw the rock in the middle here and the radii spreads out like this. And now what we're looking for here is the rate at which that area changes. Okay, so what do we know? Well, okay, first of all, we know we're looking for the area of a circle. Okay, so there, pi r squared. Okay, maybe I'll zoom in a little bit here. Okay, so pi r squared is our formula for the area of the circle. We know, or sorry, what we're looking for here is dA by dt. What we want, okay, is the rate of change of area with respect to time, and that's that dA by dt, that ratio of differentials there. We know that the radius is increasing at 4 centimeters per second, so we know dr by dt is 4 centimeters per second, and we're looking for this at the specific instant when the radius is 20 centimeters. Okay, so we know the equation. We're looking for dr by dt. Sorry, we have dr by dt. We're looking for dA by dt, and we know a specific value for r that we're looking for here. So what we're going to do here is we're going to use that relationship that relates the derivative we've got to the derivative that we're looking for, and that really is the essence of a related rate. Okay. We take the equation that connects those two, and we're going to take the derivative so that we can compare the changes of those specific variables here. So we start with a is equal to pi r squared, and now we're going to take the derivative implicitly with respect to t. Now we've got to do it implicitly because I don't see t in this equation here. Now bear in mind, pi is a constant, it's not a variable here. So we will get dA by dt will equal 2 pi r dr by dt. Now it's interesting, look at that. The derivative of the area of the circle is the circumference of the circle. Oh, that's really kind of neat. Okay, I like when stuff like that pops up. Now, we're looking for dA by dt. So now what do we know here? Well, we know that the radius at the specific instant we're looking for here is going to be 20. And we know that dr by dt, we were given this earlier, is going to be 4. Okay? So we've got 2 times pi times 20 times 4. Okay, so what do we got here? We've got, multiply that together, it looks like it's going to be 160 pi here. And we could leave it like this in exact form here. This would be 160 pi centimeters squared per second. Or we can evaluate that to really whatever point of accuracy or point of precision that we want there. Maybe we take it to the nearest tenth, and this is going to be approximately 502.7 centimeters squared per second. Okay. Now, one of the things I want you to notice now that we've gone through this, just a little thing here, but it makes a huge difference. Notice when I plugged in the value of the radius here. One of the more common mistakes made with related rates is for people to do this. Okay, they'll go, we know that area is pi r squared, and then what they'll do is they'll plug in, well, immediately we know that the radius is 20, and so we get area is equal to 400 pi. And then they know that they got to take the derivative of this, so they get dA by dt, and then they look at this part right here, and it gets a little confusing because what's the variable? Well, there is no variable. Technically, that's a constant, so the derivative of that would be 0, and that leaves you wondering what is going on here. That's because what we do here is the calculus that we're dealing with here is giving us the rates of change, or the relationship between the rates of change of these variables here. Don't plug in that specific value until after you've taken the derivative. Okay, any value that you plug in prior to the derivative, you are implying that it's a constant value. So don't do that. If you're dealing with a variable, plug the value in after the derivative. This is the way you do it. Don't worry about this right here.